first one, titanium-44, it's just an element, is a radioactive isotope such that every 63 years its mass decreases by half. Here is a formula you have to know. It's the T over P one that we just did. Capital A equals lowercase a, 1 plus or minus r to the T over P power. So, just from that first sentence, such that every 63 years its mass decreases by half, what number do you know you can plug in for something? Just give me something to start with, Natalie. Its initial mass is what? Yeah, it should be what number? 100. You read to the second sentence. I said the first sentence, but you're right. She went on to the initial mass is 100, so that's your lowercase a. Numbers in the first one. Morgan? It's decaying, so that's 1 minus. Vince, give me a number that can go in for something. No, 63 is not your rate. Rates are percentages. Where does 63 go? Haley? No. T is the duration of time we're waiting from the starting amount to the final amount to see how much is left after a certain number of time. Jason? R is 0.5 because we're decreasing by half. And we're decreasing by half every how often. That goes in for P, exactly. So that's T over 63. 63 is your P. Write a function that will give the mass of the sample. That's it. We've got it. Then they're going to ask us to use it. Scientists sometimes use the average yearly decrease in mass. Now, we don't have the average yearly decrease. We have the 63-year decrease, right? So we don't have the average yearly decrease, but sometimes scientists use it for estimation purposes. Use the average yearly decrease in mass. Okay, so now we've got to convert this to average yearly. So when we do that, we're just going to plug in a 1. And we're going to reconfigure the rate. So we're not going to touch the final amount. We're not going to touch the original amount. But we're going to retype in 1 minus 0.5 to the 1 over 63 power, which is going to give us a new base of 0.989. I'll just write the whole thing because it's amazing what estimating, cutting off like the nearest thousandth will do. So we just changed that to the 1-year rate. So we're only losing approximately what percentage per year? I mean, if I were to round this, that would be like 0.99. What percentage am I losing per year? 1%, right? 0.01, which is 1%. So they want us to use that one for estimation purposes. So use the average yearly decrease in mass of the sample between year 0 and year 10 to predict the amount of sample remaining after 40 years. So we're going to use this estimation. Well, we'll use this one to see what's left after 40 years. So we're just really going to plug in a duration of time of 40 years and see what the final amount is left. So 100.98905799681. And just put it into the 40th power. So 100. I already have that number on my calculator, so I can just grab it to the 40th power. So your final amount would be 64.4, approximately. I don't love this question. I find this whole, and I kind of just hustled over it. The year 0 to year 10 average, I think it's pretty terribly written, which is why I put it on the review sheet so we could review the concept, but not on the test because it does not read nicely at all. So just the idea of making an equation, sometimes having to change the rate to a yearly rate, using those equations to see what the final amount left is going to be under certain circumstances. That's just a word problem. Number 2, house purchased 5 years ago for $100,000 was just sold for $135,000. Approximate the annual growth. What type of equation is this? We've got, because they didn't give us a formula, we've got your basic exponential growth or decay, which we just used above. There's a compound interest option. Is this compound interest? No. And there's a PERT option that you're looking for. What buzzword? Continuous. And we don't have that either. So this is just, again, that formula. What numbers can we plug in where? Let's start with the 5 years ago. A house was purchased 5 years ago for $100,000 and just sold for $135,000. Where would the 5 go? Jason? P? So something is changing by a rate every 5 years? No. They want the annual growth rate. So they want to know the rate every 1 year. This 5-year time frame isn't the way that the rate is changing every 5 years. That's the duration of time we waited from start to finish. That's your T. Where's the 100,000 go, Alexa? Lowercase a, good. And 135 is Lucas B? Capital A. So we have 135,000 equals 100,000. 1, did it increase or decrease? Increased in price. And that took 5 years for that to happen, and we're looking for the annual growth rate. So we're just solving for R here, which is it's not an exponential equation because the R is not in the exponent. We just need to get that all by itself. So we still need to get rid of the 100,000 first, which will give us 1.35 equals 1 plus R to the 5th power. I can't break into those parentheses until I get rid of 5. How do you get rid of a numerical exponent? Yeah. Logging takes a variable out of an exponent. We don't have a variable in an exponent. It's been a while since we've done this, Chris. You raise it to the reciprocal. Like when you're trying to solve an x squared, you square root both sides, which is like raising it to the 1/2. If you're raising it if it's being raised to the 5th power, you raise it to the 1/5 power to get rid of it. And 1.35 to the 1/5 power is going to be a 1.0618 crazy number. But now it's pretty easy to get the R all by itself. Just subtract 1 over. They don't give us solving for that R very often, I'll be honest with you. But if they do, you have to know how to get rid. We started the chapter with this, believe it or not. That was like on some notes in the beginning of the chapter. It just doesn't come up often. So the rate is to the nearest percent. How many percent? Well, it just says nearest percent, so I'm just going to say 6%. Okay? Your homework is to do the review packet. Oaksy dokes. I'll probably send out solutions later today because they're not on the bottom. Sorry about that.
Yeah.